All right, let's dive in. Today we're talking about a seriously powerful performance trick you can add to your Swift toolbox, implementing your own custom copy-on-write behavior. This is how you can get your own data types to be just as smart and efficient as Swift's built-in collections. So, let's get right to it.
You know the feeling, right? You've got the struct and it's holding a ton of data. Maybe it's a big image buffer or some complex model. You pass it to a new variable, maybe into a function, and boom, your app just stutters or hangs for a second. Well, that's that hidden performance tax of copying large value types. So what's actually going on here? See, by default, when you copy a struct, you're doing what's called a deep copy. That means you are literally duplicating every single byte it holds. And as you can imagine, that can be super inefficient. But here's the thing. Swift's own collections, like array and dictionary, they're way smarter. They use a special technique to share their underlying data until it's absolutely positively necessary to make a duplicate. And this right here really lays out the difference. On the left, you've got this brute force approach. Every time you assign it to a new variable, you're doing a full-blown, expensive duplication. That puts a real strain on your memory. But the copy-on-write approach on the right, it's all about working smarter, not harder. The data is shared by default, and a copy is only made at the last possible second, right before a change is about to happen. This is exactly the kind of efficiency we want.
Okay, so let's put a proper name to this. Copy-on-write, or CoW for short, is basically a strategy of lazy copying. Think of it like this. You share a link to a Google Doc. Everyone's looking at the exact same document, right? But the moment someone actually starts editing, bam, the system makes a private copy just for them to mess with, leaving the original untouched for everyone else. That's pretty much copy-on-write in a nutshell.
And this is the really cool part. This powerful technique isn't some secret magic sauce that's locked away and only used by the engineers working on the Swift standard library. You, right now, have all the tools you need to build this exact same behavior into your own custom structs. So how do we pull this off? Well, it's actually a pretty straightforward recipe. Let's walk through the 4 main steps you can follow to add copy-on-write to pretty much any struct that manages a large chunk of data.
Here's the game plan. First up, we take our heavy data and wrap it inside a class. And this is the secret sauce right here, because classes are reference types, which means lots of variables can all point to the very same instance in memory. Step 2, our main struct, the thing we're actually going to use in our code, will just hold on to an instance of that storage class. And then, the absolute crucial step. Before we ever change the data, we add a little check. We ask, is anyone else using this storage? If the answer is yes, then we create a fresh copy just for ourselves before we make the change.
You know, this whole thing really hinges on asking one simple question. It's the critical decision point that determines whether we do a costly copy or if we can just get on with our day.
And that question is simply this. Is the data I'm about to change being used by anyone else? Or, to put it a bit more technically, is it uniquely referenced? If we're the only ones holding on to it, great, we can change it. But if it's being shared, we have to make a copy first.
And this is where Swift really comes to the rescue. We don't have to build our own crazy reference counting system or anything like that. Nope. Swift just hands us this awesome little function called isKnownUniquelyReferenced. You just pass it a reference to your storage class, and it gives you back a simple true or false. True if you're the sole owner, false if it's being shared. This function is the magic ingredient.
Okay, enough theory. It's great and all, but let's see how this actually plays out with some code. We'll walk through a quick scenario to really see this logic in action.
So let's say we create an instance of our cool new buffer, A. Then we just do var b equals A. Now pay attention here because this is the key. Nothing got copied. No big, expensive data duplication happened. In memory, both A and B are pointing to the exact same underlying storage object. It's super fast and incredibly memory efficient.
And this is where the magic happens. We go to change B, right? We call append to add the number 4. The very first thing that append method does is it asks that question, is known uniquely referenced? And because A is still looking at that same data, the answer is false. That's our trigger. So then, and only then, does our code make a brand new copy of the storage just for B and modifies that new copy. And the result? A is completely untouched, still holding its original data, while B gets the new value. The expensive copy only happened at the precise moment it was needed.
Okay, so we've seen how it works, but let's really nail down why this is such a game changer for your own code. What's the real payoff here?
The payoffs here are huge. First off, it's just way more efficient. You stop making all these expensive, unnecessary copies. It's also much safer, because you're making sure that changes to one variable don't mysteriously affect another. You get true value semantics. That's just a fancy way of saying your custom type now behaves just like you'd expect a built-in Swift array to. And all of this makes your code so much more predictable and easier to reason about. And look, this isn't just some weird academic trick. You can use this right now on large data models you're pulling from an API, on custom image or audio buffers, on caching layers, basically anywhere you have a struct that's holding a lot of data that gets passed around your app.
So, I'll leave you with this question. Next time you're in your own codebase, take a look around. Where is that hidden performance tax slowing you down? And where could implementing copy on write be the thing that saves the day, making your app faster, safer, and just plain better? Thanks for joining me.